Yesterday, we defined something new, radioactivity. You've heard of that term before, but you might not have known what it is before. Radioactivity is a natural process. It's a spontaneous process. It's a random process, which means it happens when it wants to happen, and it happens on its own. We don't control it whatsoever. It's a process in which a nucleus decays into something else. A nucleus changes into something else. It's not chemistry where one atom of one element combines with another atom of another element to form whatever compound. This is when we're changing the element itself to something different. Now, the radiation that comes from this, the particles that come out of this as a result of changing one element to another element, this process of radioactivity, or what we call ionizing. And ionizing just means that it will turn atoms into ions. It'll remove electrons from atoms, which means that you don't have neutral things floating around anymore. You've got charged things floating around. And sometimes, not always, but sometimes that can lead to a whole host of problems. Right? We talked yesterday about when you have ions, say, floating around inside your body, it leads to maybe chemical reactions that aren't supposed to happen inside your body. And chemical reactions inside your body that aren't supposed to happen can lead to radiation sickness. They can lead to anything from vomiting to blood coming out of your eyes and ears to almost instant death. All kinds of problems, to cancer, right? A slower issue. Bottom line is, this process of converting one element into something else, of one nucleus decaying into something else, will always produce these little particles that we call ionizing radiation that can lead to these reactions that can lead to things that aren't supposed to happen. There's three types of radioactivity that we talked about yesterday, and we'll real quickly once again go through those three types of radioactivity. The first type is called alpha decay. This is when we have a big nucleus, a big element. We're talking about something like uranium, which has an atomic number of 92 protons, 140, 145 neutrons. It's big. When we have a big element, sometimes it's not stable, and as a result of it not being stable, it will sometimes release a much smaller particle called an alpha particle. That alpha particle, by the way, chemically identical to a helium nucleus. Sometimes you might see it written like this, 4,2 alpha. Sometimes you're going to see it written like this, 4,2 helium. Exactly the same thing. This is not the radioactive nucleus. This is the ionizing radiation that's produced as a result of the radioactive nucleus decaying. It decays into something and then releases the alpha particle. Now, when does this happen? When does this happen? This happens when we have too many protons. Too many protons relative to the number of neutrons. So here's the deal. In the nucleus, you've got two forces. There's actually three forces acting in the nucleus, but two forces that we care about right now. The two forces that we care about are what we call the strong nuclear force which is an attractive force. That keeps the protons together, it keeps the neutrons together, and it keeps the protons and neutrons together. It's the glue that holds the nucleus together. It pulls everything towards each other. Okay, we got a whole bunch of people in a classroom right now. If we were to join hands and pull on each other, that would be the strong nuclear force. Okay, there would be boys pulling on boys, girls pulling on girls, boys pulling on girls. In the nucleus, you've got protons pulling on protons, neutrons pulling on neutrons, and protons pulling on neutrons with this strong nuclear force. It's what keeps the nucleus together. But we've also got this electric force or electrostatic force. It's a repulsive force. It can also be attractive, but in the nucleus, it's a repulsive force. It acts between proton and proton. It doesn't act, by the way, between proton and neutron. Remember back in Unit 2, we said that an electric force acted between a charged object and a neutral object, not between a proton and neutron, because that neutral object has to be able to develop a separation of charge, and you can't do that in a neutron. So it acts between proton and proton. And as a result of that, it's got to be a repulsive force between proton and proton. Yeah, Nick? That's a good question. I said there's 3 forces in the nucleus. There's actually 4, okay, because that 4th force is the gravitational force. But that's those other 2 forces beyond these 2. The other force we call the force of gravity, and the other force we call the weak nuclear force. They're relevant for this, for what we're talking about right now. Now, if the strong nuclear force, which is an attractive force, is bigger than the electrostatic force, then the nucleus stays together. But if the repulsive electrostatic force is bigger, then the nucleus breaks apart. It's as simple as that. If we're all holding hands and pulling each other together, okay, the strong nuclear force is big. But if we're pushing each other apart, pushing each other away from each other, then the repulsive electrostatic force is big. If the repulsive force is bigger, we don't stay together. If the attractive force is bigger, we do stay together. It's as simple as that. Now, when you have too many protons, you get too big of a repulsive force. That's what it boils down to. Too many protons, too big of a repulsive force. And the repulsive force ends up winning and the nucleus breaks apart. And as it does that, it gives off an alpha particle. Most of the nucleus stays. Uranium-235 may turn into thorium-231. It's still a big nucleus, but it's a little bit smaller than it was before because now you're missing 2 protons and 2 neutrons. Beta decay, we actually break that down into 2 subcategories. There's the first one, which is beta negative, which, by the way, a beta negative particle is chemically identical to an electron. And we talked yesterday about where the electron comes from. How can we get an electron out of a nucleus when there are no electrons in the nucleus to begin with? The other type of beta decay is beta plus, or beta positive decay, which is chemically identical to not an electron, but we could call it an anti-electron, antimatter, or we can call it, it's another word for it. I'm positive you know this. A positron. Yeah, it's a positron. An electron, or the antiparticle of an electron, which is a positron. Now, when you have beta negative decay, it occurs because you have too many neutrons. But it doesn't have anything to do with these forces, the strong nuclear force and the electrostatic force. Rather, when you have too many neutrons, it's energetically unfavorable. So the nucleus changes a little bit. It changes a neutron into a proton. That changes the ratio of neutrons to protons. It improves the energy, kind of improves the balance of things, right? You get too many neutrons, and now you have 1 neutron less and one extra proton, then the balance is much better. Now, you got to be careful here. It's such a fine balance here, right? You get too many protons, and then maybe this happens. You get too many neutrons, and then maybe this happens. There is something like 2,500 different isotopes of elements that exist. There's what, like 115 or so elements? There's about 2,500 different isotopes. The vast, vast majority of those isotopes are radioactive. The vast majority are radioactive. Why are the vast majority radioactive? Because the balance has to be so perfect. You get too many neutrons, one thing happens. You get too many protons, something else happens. You got to have a perfect balance, right? Here, if you have too many neutrons, the energy isn't quite right, and we change a neutron into a proton to get 1 less neutron and an extra proton. But the problem is, we started off with a charge of 0 here. Now we get a charge of +1. That doesn't work out. It violates the law of conservation of charge. So we have to have an electron produced here as well, which has a charge of -1, to make the law of conservation of charge work. Now this electron, the proton, stays behind in the nucleus and just changes the nucleus into something else. We had something with an atomic number of maybe 6. Now we have something with an atomic number of 7 because we have an extra proton. And then the electron leaves the nucleus. That's the beta particle. We said a few minutes ago, as we started this, How do you get a beta particle? How do you get a negative electron out of a nucleus when the nucleus doesn't have any electrons to begin with? Well, we make one. We change a neutron into a proton and an electron, and then the electron just leaves. That's the beta particle. Beta plus is a similar process, except here we have, with beta plus, too many protons again. But the result of too many protons here isn't the same effect as when we had alpha decay. And it's a different reason why the decay occurs. Up here you had too many protons because the forces weren't quite right. Or too many protons which resulted, I should say, in the forces not being quite right. Here we have too many protons, which doesn't give us problems with the forces, but gives us problems with the energies again. Once again, it's energetically unfavorable. Now the energy just isn't quite working again. It's not the forces this time. Same problem, but different reason. It's not the forces this time, it's the energy this time, and it isn't quite working out. So what do we do if we got too many protons and the energy isn't quite working out? Let's change a proton into a neutron. But that's a problem because we had +1 to start off and 0 charge afterwards. So we got to produce something with another charge of +1 so that the law of conservation of charge holds. That's going to be a positron. Well, the neutron stays behind in the nucleus. Now we have one less proton, so we've changed the element into something else. But the one less proton, one more neutron, but the electron, or I should say the positron, the anti-electron, it's not supposed to be in the nucleus, so it leaves. That's the beta plus particle, or the positron that leaves here. And then finally, gamma decay. You saw yesterday that this was just pure electromagnetic radiation. 0 protons, 0 electrons. It's just EMR. It's energy. And it comes from something else having already happened. The nucleus after beta decay is left in an excited state. Okay, the nucleus is kind of jittery, kind of excited, but it goes back down to its normal state. As it goes back down to its normal state after something like beta decay has occurred, it has to give off energy. Okay? As it goes down, it relaxes. Whew. Take a deep breath. Whew. Breathe out. Gives off energy. Okay? And that energy that it gives off is in the form of electromagnetic radiation, which is a gamma ray. If you remember back in our last, the very first day, we talked about the 7 types of EMR, and we said that visible light was produced by transitions of electrons in atoms, and X-rays are produced by rapidly decelerating electrons. And gamma ray was produced by nuclear decay. When beta decay happens or something like that, the nucleus is left in an excited state, and when it goes back to its normal state, it gives off EMR. And then finally, this is where you ended up with yesterday. We talked about 2 properties of each of these, alpha, beta, and gamma. Go ahead. Yes, there's a whole bunch of situations where it can happen as well. But in this context, we're talking about it in the context of radioactivity here, right? But there are other situations where it can happen as well. Basically, when you have that nucleus excited for one reason or another, and it goes back down to its regular state, then a gamma ray would be released. Yes. Yesterday we talked about the ionizing potential of these 3 types of ionizing radiation. Remember, we said they're all ionizing radiation. What ability do they have to ionize matter? Like how easily do they change atoms into ions? And then how well do they penetrate matter? How well do they go through matter? Well, here's the deal. The alpha particles have a very high ionizing potential. Okay, alpha particles can ionize matter easily, which is bad news, okay, if we're exposed in the wrong way to alpha particles, because it easily turns atoms to ions. And then those chemical reactions that we talked about, those undesirable chemical reactions start happening pretty easily because we get lots of ions formed as a result of these alpha particles. The good news is, even though they ionize matter really, really easily, They have the lowest penetrating power of the three. So if they get in our bodies, they do lots of damage. But they have a tough time getting in our bodies because one or two sheets of paper can shield you from alpha particles. If you're exposed to alpha particles somewhere where you're dressed, where you have clothes on, your clothes will shield you from the alpha particles. You have nothing to worry about. Okay? If you're exposed to alpha particles when you're covered up by fabric or by something like that. Okay? So it's generally not a problem in that regard. The main problem would tend to occur if you happen to consume not alpha particles, but you consumed something that was radioactive. Like you drank water that was laced with uranium-235, or you ate a cow, you ate beef that ate grass, that grew in soil that was contaminated with uranium-235. When you consume the radioactive nucleus, then it decays in your body. And then it doesn't have to get through your clothes and through your body because it's in there when it decays and turns into an alpha particle. That's when alpha decay would be a problem for you when it's produced inside your body as opposed to just being exposed to it. Now, gamma rays have, I don't want to say they have a low ionizing potential. They don't, but it's the lowest of the three. But the flip side of that is that they have the highest penetrating power of the three. The alpha particles will be stopped by a sheet or two of paper. Gamma rays will penetrate several centimeters of lead or concrete. You got to be shielded significantly from gamma rays if you don't want damage to occur. Gamma rays are what they typically use when they talk about radiation therapy for cancer treatment. Okay? They have a high penetrating power. They'll go through your body. They'll attack the tumor. Problem is they also attack healthy cells. That's why people get sick when they have radiation therapy for cancer treatment, right? They try to minimize that effect by firing gamma rays in relatively low intensity gamma rays from different directions. Let's say I got a tumor in my stomach. They'll fire a gamma ray this way, 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 and from all different angles at the same time, so that each of the gamma rays will cause a little bit of damage. This gamma ray causes a little bit of damage to the tumor, but also the healthy cells before and after. This gamma ray causes a little bit of damage to the tumor, but also the healthy cells before and after. But the only thing that overlaps in that deal with all these gamma rays is the tumor, right? They intersect at the tumor. They all come together, and it's like we get constructive interference or lots of damage at the tumor and only a little bit of damage both before and after the tumor in the various places. So it does damage, but to healthy cells, but it's it's a trade-off it's a risk that we take, right? Beta decay are kind of the fence sitters, right? They ionize radiation better than gamma, and they penetrate matter better than alpha decay. So we kind of rank them 1, 2, and 3 in terms of ionizing power. We rank them 1, 2, and 3 in terms of penetrating power, but it's a reverse order. All right? Make sense? All right. Today we're going to talk about not so much the types of radiation and how they're produced like we did yesterday and like we just reviewed here today. But today we're going to talk about the actual reactions that take place. We call it transmutation equations or transmutation reactions. Transmutation is a term that describes the conversion of one element to another. Isn't that what radioactivity is? No, radioactivity is actually an example, a type of transmutation. Okay, radioactivity is the process by which transmutation can occur. There's a couple other ways in which transmutation can occur as well, where we convert one element to another. So we're not talking exactly about radioactivity right now, but it's real close. Okay, radioactivity is a type of transmutation or a way in which transmutation can occur. So is nuclear fission, which we'll talk about real soon. Nuclear fusion. something called artificial transmutation. All of those are ways in which transmutation can occur, but we focus, of course, on, at least right now, on radioactivity. We're going to write nuclear equations, or sometimes we call them transmutation equations, that are kind of a little bit like chemical equations. We're showing what's happening, but instead of balancing the elements and making sure that we have 6 atoms of oxygen on this side and 6 atoms of oxygen on the other side, and 3 atoms of carbon on this side and 3 atoms of carbon on the other side, the elements change now. So that's all off. Now what we got to do is balance not the elements, but we got to balance what we call the nucleons, the protons and neutrons. We got to make sure that the mass numbers and the atomic numbers balance out. So it's similar to writing chemical equations, but yet it's not the same as writing chemical equations. A couple examples for you here, guys. I'll tell you what, you got to write this out, but just write it point form just to save yourself a little bit of time, okay? It doesn't have to have every single word that's in the question here. We want to write the nuclear equation for the transmutation of radioactive isotope radium-226. It's undergoing alpha decay. Okay, it undergoes alpha decay. It produces an alpha particle. Why does it produce an alpha particle? Well, because we have too many protons. Alpha decay occurs when we have too many protons. The repulsive force is too big. The attractive force is too small. The nucleus breaks apart. And when it does, an alpha particle is the victim of it all. The alpha particle is the part that has to leave. And then you're left with something else, something a little bit smaller than radium-226. Not much, but a little bit smaller than radium-226. So what is this going to look like? Well, we're going to start off with radium-226 as our, in chemistry we'd call it a reactant. In nuclear physics we usually call it a parent. Okay, this is our parent nucleus. If you call it a reactant, I don't really care. Okay, sometimes I call it a reactant myself, but technically it should be called a parent nucleus. It undergoes alpha decay, so we've got to have an alpha particle here, but because it's decaying into an alpha particle, the alpha particle is going to appear on the right-hand side, not the left. Okay, if I drew it on the left-hand side here, said radium-226 plus alpha, that's not decaying into an alpha, that's having an alpha that already exists, right? An alpha before the whole deal starts. We get an alpha particle produced after this process takes place, plus something else. Well, we can't add alpha particles to the left side to make the alphas balance, or radiums to the right side to make the radiums balance, but what we can add is mass numbers and atomic numbers to one side or the other in order to make those numbers balance, right, Laura? What we're going to do first is look at the atomic number. We have 88 on the left-hand side. We have to have 88 on the right-hand side. So we're going to say 2 on the right-hand side plus 86 gives me 88. Okay, it means we have 88 on both sides. The numbers have balance now. Let's look at the mass number. 226 on the left-hand side. Well, we have to have 226 on the right-hand side. 4 plus 222 is equal to 226. And I think if you look at your periodic table, I think you would find that the atomic number 86 is Rn, radon. You don't have to memorize what element is what. You just have to be able to find it on your periodic table. The periodic table in the back of your data booklet, there's 2 numbers for every element. The bigger number, we never care about. The bottom number, or the smaller number, I should say, is the number that we care about. You're looking for atomic number 86, and I think 86, sure enough, it is Rn, radon. So there you go. Now, I'm going to ask you to look somewhere else on your data sheet for a second here, okay? Everybody haul out your data sheet if you haven't already. Flip the page back to the second page where it just says physics data sheet at the top. In the bottom left-hand corner, you see a list of 10 physics principles. You're going to get a couple questions on your diploma exam where you have to identify which physics principles you've used. And we'll do a couple examples of that over the next few weeks leading up to our diploma exam. But I want to point out right now that by balancing this equation, we've used 2 physics principles. Okay, 2 physics principles. What 2 physics principles do you think we've used, if you're looking at this list, to balance this equation? 0 through 9, which 2? If you can come up with 1, let's hear it. Okay? Principle 7 is conservation of charge. Yes. So when we said 88 goes to 88, that's conservation of charge. Because really you're saying, look, I got to have plus 88, and I got to have plus 88, right? 88 protons. Yep. Good. The other one is conservation of nucleons. A nucleon is a proton or a neutron. We have to make sure that the number of protons and neutrons balance here. So this is going to be conservation of nucleons. So if you happen to get that question on an exam that says, okay, balance it, but then it asks you a follow-up question, which 2 physics principles did you use to balance it? The answer is principle 7 and principle 8 there. No. Conservation of mass energy would be whenever you use E equals mc squared. Okay? We'll talk about these over the next couple of weeks, so don't panic if you're looking at a couple of these and thinking, oh, I'm not sure when I'd use it. You will. It's not very hard. It's just a matter of us going through it for a little while. All right, let's do another one here. This, by the way, it says transmutation of radioactive isotope lead-214 undergoing beta decay. It should say beta negative decay. We should specify whether it's beta negative or beta positive, because there are the 2 types, right? I've got lead-214. It undergoes beta decay. And that happens because we have too many neutrons. The forces aren't the problem now. The energy is the problem. You have too many neutrons. It's energetically unfavorable. What do? You change a neutron into a proton and an electron. Here's the electron that's produced. Got to be on the right-hand side because it's produced. My parent nucleus is lead-214. What's my daughter nucleus? Or my product? Well, 0 plus 214 gives me 214. Negative 1 plus what gives me 82? Be careful here. Negative 1 plus what gives me 82? Or 83. Probably the most common mistake that I see in this unit would be minus 1 plus 81 gives me 82. It doesn't. Now, if we look at our periodic table to find atomic number 83, I believe it's bismuth, Bi. Now, one more little thing here. In 1930, a guy named Wolfgang Pauli is looking at this beta negative decay and beta positive decay for that matter as well, and comes to the conclusion that something's missing. There's some energy missing here. So he hypothesizes the existence of some other particle that carries that energy. Calls it a neutrino or an antineutrino, depending upon what reaction we have. For a beta negative decay, he would have added an antineutrino. Okay, this is a symbol for neutrino with a little line over it, means an antineutrino. If it was beta plus decay, he said there had to be a neutrino there. He never actually saw these neutrinos or antineutrinos or detected them, but we have since that. In fact, there's a neutrino observatory in Canada, in Sudbury, Ontario. Do you know what Sudbury, Ontario is famous for besides neutrino observatories? Well, it's the biggest thing that they're famous for would be if you ever driven through Northern Ontario, you get to Sudbury and there's this. I get a kick out of it whenever you drive across Canada or the United States for that matter. Every town has their own special thing, right? Vegreville has the world's largest Easter egg, and wherever has the there's a place in New Brunswick that has the world's largest potato, and then there's somewhere else that has the world's largest whatever. In Sudbury, they have the world's largest nickel, like coin. It's massive, and the reason for that is because they're famous for nickel mines. They mine nickel. in Sudbury, and nickel is found like deep underground. And what they've done is converted some of these abandoned nickel mines into neutrino observatories. These tiny little particles can be observed in these neutrino observatories deep underground. And the reason they use these mines deep underground is because nothing else can get through the ground. It's all rock, and it's deep underground. If they detect something down there, then it's a neutrino. Right? Nothing else makes it through. Neutrinos can make it through the Earth to get down there. Nothing else can. So they basically isolate themselves from the whole outside world, and then if they see something, then it must be a neutrino or an antineutrino. How come? So when a neutron, you mean? Okay, so when a neutron decays, let's look at this again for a second here, and then I'll come back to that, okay? Here we've got 82 protons, right? Here we have 83 protons. Okay? Here we had, what, 100 and, what's 214 minus 82? 132? Is 132? 132 neutrons. Here we have 131 neutrons. We have one less neutron, one more proton, right? So a neutron has changed into a proton and then the electron, right? But you're saying, why doesn't the neutron change into an electron and a positron instead of an electron and a proton? We're going to look at the mass on your data sheet of an electron, of a neutron, and a proton. Top right-hand corner of your data sheet. The mass of an electron is 10 to the minus 31 kilograms, right? The mass of a proton is 1.67 times 10 to the minus 27. The mass of a neutron is 1.67 times 10 to the minus 27. If you've taken chemistry, you might know that a neutron actually weighs a little bit more if we keep going. It weighs a little bit more than a proton. So if we have a neutron that has a mass of 10 to the minus 27, we can't get two things out of it that both have a mass of 10 to the minus 31. That make sense? We have to have something that's comparable in mass. Okay. So balancing out these equations, make sure that you balance out the atomic number and the mass number, and if it's beta negative decay, make sure you put an antineutrino. If it happens to be beta positive decay, make sure you put a neutrino in there. All right? We're not done yet. Don't pack up, please. Let's take a look at C here, okay? We're going backwards this time. We're not told what kind of nuclear decay this is. We're shown part of the reaction. We got to figure out what kind of nuclear decay it is. Let's figure it out though. 13 on the left side, 13 on the right side. 13 plus 0 gives me 13. 6 plus what gives me plus 1? 6 plus what gives me 7? I think I just gave it away. I think I misspoke and gave it away. What is it? Plus 1. Plus 1, not minus 1, right? 6 plus minus 1 will give me 5. 6 plus 1 gives me 7. This is going to be a beta plus particle. This is beta positive decay, right? It's a positron that's emitted. And what do we get in addition to the positron? Not an antineutrino, but, sorry? No, just a neutrino. Just a plain neutrino. Neutrino, and then there's the antineutrino, which is the antiparticle of a neutrino, kind of like the positron is the antiparticle of that. Hold on, let's just do one more quick one here, okay? This is what we call an artificial, just do A here, okay? An artificial transmutation equation. This is not radioactivity. Okay? We're making this happen. We're firing an alpha particle at nitrogen here. It's not decaying into an alpha particle. We've got an alpha particle already that we're colliding with a nitrogen. 14 plus 4 gives me 18. 17 plus 1 gives me 18. 7 plus 2 gives me 9. 8 plus 1 gives me 9. What's that? Got to look on your periodic table. If it's not an alpha or beta particle, you got to look on your periodic table. What has an atomic number of 1? Hydrogen. You get a hydrogen nucleus produced here. All right, here's your homework for tomorrow in addition to your quiz. I'd like you to work at check and reflect questions on page 810. Number 1, 3 to 7, and 9 and 12. So 1, 3, 4, 5, 6, 7, 9, and 12. Please get those done for tomorrow.